A 0.4 kilogram mass on a 1.2 meter rope is swung in a vertical circle at a speed of 32 meters per second. Find the tension in the rope when it's 30 degrees above the horizontal. Alright, now I've done a problem like this before. That time it was a horizontal circle. This one is a vertical circle, so you're swinging a rope or something so that the circle is upright. That is a little more complicated because gravity affects the tension in the rope, and it depends on where you are on the circle, whether gravity increases or decreases the tension. So in this case, we are at the point 30 degrees above the horizontal. So let's draw a picture. Here's a horizontal. Just a line for reference, it's not the ground or anything. And the circle is vertical, so it's going around like this. Okay. And so we are 30 degrees above the horizontal. So that would be at this position. Here's our mass. Right? And okay, so that's pretty much our picture. I can put my angle in right here. That is the theta of, we'll call it theta, equals 30 degrees. Alright. We also know the length of the rope. I'm going to call it R because it stands for radius. L would work too, but I like radius. So we drew our picture. The next step is a free body diagram. Here's the mass. I'm just going to give myself an idea of where it was moving. Ah, yes, and I should mention over here it has some velocity. Okay. So the forces on this guy, well, we're going to have tension this way, and we're going to have gravity this way. Alright, and those are the only two forces. Now, we need, for a good free body diagram, to define our coordinate axis. Now, I've mentioned before the trick to circular motion problems. When there's a circle, when it's moving in a circle, you need to make one of your axes point toward the center of that circle. I like to call it the C-axis. These letters don't really matter, of course, so I'm going to call it the C-axis, and I'll just call that one the Y-axis. So I drew a free body diagram. The next step is always Newton's second law equations. Sum of the forces in the y direction equals mass times acceleration in the y direction. And the sum of the forces in the the sum of the forces in the c direction equals mass times acceleration in the c direction. Alright, so I happen to know that the c direction of where the action is, so I'm going to start with that one. If you ever have an inkling that you might not need another equation, one of the other ones, just start with the one that you think you need. You can always come back to the remaining equation, and we'll see what happens in this case. So the sum of the forces in the c direction equals mac. Now that is the centripetal acceleration because it's the acceleration in the direction of the center of the circle. So it's mv squared over r. Centripetal acceleration is by definition v squared over r. You may know it as radial acceleration. So just imagine that that's what I'm writing here for AC. They're exactly the same thing. Alright, now I've listed out the definitions here. This is sum of the forces is MAC. AC is V squared over R, but also it's literally just the sum of the forces. So in the C direction, I have the tension, positive tension, but I also have a component of gravity. Let's see. If I break gravity into its components, like this, then we can figure out the C component of gravity. So let me just write, it looks like it's going to be plus mg's C component. And we'll figure out what that is. So to find mgc, we're going to need to know an angle in this gravity's force triangle here. So mgc is this side, and this is my mgy. A little small there. So we'll have to figure out either that angle or that angle, and then we'll be able to use right triangle trigonometry. So we'll have to reason it out from this picture over here, which could be cleaner. If you were to draw a line straight down, that makes this not theta, but 90 minus theta right here. I'll just call that phi for a second so we can keep track of it. 90 minus theta there, that's the angle between the vertical and the rope. Over here, that is the vertical. MGE labels the vertical, and tension is also the direction of the rope. So the angle between those two is also that phi, 90 minus theta, which means that this is theta here. Alright, because of the properties of a right triangle. And you can confirm that for yourself. But what that means for us is that MGC is going to equal MG sine of theta, right, using right triangle trigonometry. So what we're looking at here is mv squared over r is equal to t plus mg sine of theta. Now let's just recall what we're doing. We're supposed to find the tension in the rope. So let's go ahead and solve this for tension. T equals m v squared over r minus g sine theta. I subtracted this term over to the other side, and I factored the mass out of both of them. Let's see if we know these things. We know g, of course. Theta, I believe, was 30 degrees. Do we know v and r and m? R is the 1.2 meter rope. M is 0.4 kilograms. And v, we do know it's 32 meters per second. So we've done it. We know all of these values, so we found our tension. So as you can see, the angle does make a difference, the angle that you're at. This, however, will answer any angle. All you have to do is define your angle with respect to this line here and plug the value into our expression, and we'll get the tension at any angle on this circle. So there is a nice centripetal or radial acceleration problem. We drew a picture, we drew a free body diagram, and used Newton's second law, and that's about it. Thanks.